Greetings. This is part 2 of the recording to show empirical work done in Guidelines for Programmers on Securing Web Application from SQL Injection and Cross-Site Scripting. The goal of the project is to prevent SQL injection and cross-site scripting on the backend of a web application and to provide guidelines to programmers in PHP and Python. This recording will show cross-site scripting only. So what is cross-site scripting? For a formal definition, a cross-site scripting attack takes place when the software does not neutralize or incorrectly neutralizes user controllable input before it is placed in the output that is used as a web page that is served to the other users. In simpler terms, cross-site scripting is a hacking technique. Cross-site scripting, also known as XSS, is a web security vulnerability that allows an attacker to compromise the interactions that users have with a vulnerable application. Cross-site scripting vulnerabilities normally allow an attacker to masquerade as a victim user to carry out any action that the user is able to perform and to access any of the user's data. If the victim user has privileged access within the application, meaning the user being the admin to the application, then the attacker might be able to gain full control over all the application's functionality and data. We will be replicating the attack on a website, and a e-commerce website with PayPal as the payment gateway. The goal is to secure the web application from reflective cross-site scripting. We will be performing a manual injection on the comment page, which is vulnerable to a cross-site scripting attack. All three attacks will be performed and they are explained in my thesis report. So the attacks are reflective cross-site scripting, stored cross-site scripting, and document object model cross-site scripting. We will be using Vega. Vega is the chosen tool for penetrating the web application, and it will also be used to evaluate the work. Let's get straight into the attack. So this is the web application. This is the comment page. So here we will be trying out a reflected cross-site scripting attack. A reflective cross-site scripting. This is a JavaScript which says alert. We could put something like this. And let's comment, and it gets reflected back at the page. So this page is vulnerable to a reflective cross-site scripting. Now for a more complex attack, so let's break down this attack. This is a document object model attack. So PayPal hack is the hack, the name given to the hack, and we say script window.location, so is the URL of the document being displayed in that window, so the URL, and document.cookie is read the cookie, so we say that read the cookie over here. So let's perform this attack. It is a DOM-based cross-site scripting attack. We say hackers. Oh, I'm sorry. So before we perform the attack, let's see what happens at hacker page. So let's go to hacker page. So in the hacker page we say get cookie, and we are storing the cookie in mycookies.txt. So as of now mycookies.txt is empty. I'm sorry, that was the readme file. So mycookies.txt is empty. Let's perform the attack. So it took us to the PayPal page, which looks real, but what the user does not know is we just stole his cookie details. So mycookie.txt, it says we've got the session ID and the session is password, and the password equal to nickel123. We just stole his password. So this is a very dangerous cross-site scripting attack. So let's just take this out. Now let's remove this from the... So we saw a DOM-based attack, and now this has turned into a stored cross-site scripting, as the malicious script is stored in the database, and every time I reload the page or come to this page, it takes me to PayPal. So the only way to stop the attack would be to delete it from the database. Yeah. So now we don't have that attack no more. Let's have we type something else. Yeah, we are saved from the attack. We shall replicate the same in the Python web page, which is also vulnerable to a cross-site scripting attack. So we will be performing a reflective cross-site scripting, and we'll get 1. So if we look back at the code, we said, okay, we said alert 1, so that is what we got. It keeps popping up because it has turned into a stored cross-site scripting, so we will have to delete it. Okay, that's done. Now we shall use Vega to check these vulnerabilities. So we say scan target, so the target is, we're targeting the PHP page at first. So contact.php is the page. We only want to check for cross-site scripting attack. So we will exclude these parameters and click finish. So Vega has found 3 vulnerabilities. Let's have a look at these vulnerabilities. So classification is input validation error. The parameter is name, and this was the code injected. It also discusses about cross-site scripting. It gives us the impact of cross-site scripting, the reputation. The second vulnerable field was post, and the third, the second vulnerable post was submit, and the third vulnerable field was message. So let's check the same with the Python web page. So we're checking the Python web page for vulnerabilities. We say we only want cross-site scripting checks. Next. So it says there is a stored cross-site scripting vulnerability going on, and it is in the comment section. So as of now, both the web pages are vulnerable to a cross-site scripting attack, and let's save them, secure this web application. At first we will have to delete these attacks from the database. So these are the different malicious code tried by Vega, so we'll have to delete all of them. So we say so we got rid of that. So now how are we going to secure the web application? So in we'll have to validate all HTML special characters, and these are these are the characters that needs to be sanitized, that is a greater than, less than, ampersand, all of these. In PHP it is done by HTML special characters, and in Python we use Flask validation. So before we do this, let us try to secure this attack, the DOM based attack in PHP. So this could be done by simply setting the setCookie function to true. So what we have been done here is the securing cookie setCookie function by default is set to HTTP equal to false. So this is dangerous and must be true to, so this cookie could be secure. Thus scripting languages do not have access to the cookies. So let's check this out. So we save it, we run the attack again on the PHP website. So we say, so we are trying the PayPal hack again. So we say add comment. Yes, the attack worked, but did the hacker get the details of the session? He got the session ID and the session equal to password, but the password value was not revealed. So we were able to stop this. Now let's completely stop the attack. So in PHP we use HTML special characters to sanitize the input. So now let's check this out. Before we do that, we'll have to delete the injected code. Yeah, now okay. So say we wanted to try the reflected cross-site scripting attack. So nothing popped up. So I'm sorry, that's a good sign. And let's try another attack too. So as you can see, it is all there, but nothing happened. We are on the same page. So let's have a look into the database. So all the special characters were sanitized. So the attack no longer works. The PHP web application is saved from cross-site scripting. We shall do the same. We'll secure the Python web application. Here we escape and encode. We'll see more into encoding later in this recording. And Flask by default saves the web application, so we are using Flask here. So we are using Flask from Flask. So Flask validation is going on the PHP web application. So let's test this out. We say hack the PayPal hack. The PayPal hack did not work. Let's try a reflected cross-site scripting attack. So we were able to secure the Python web application from these attacks. Now let's use Vega once again to validate our work. So let us confirm the database has no stored, yes, so it does not have any stored cross-site scripting, so we are ready. So let us scan. So we will be scanning the PHP website at first. So as you can see, the scan alert summary shows nothing, meaning we have secured the Python web application. Now let's check the PHP one. Okay, it says stored cross-site scripting. This is because every time Vega checks it, all the comments are stored. We must delete them. So on deleting them, we will not have a stored cross-site scripting. So we say check all. Let's run the Python web application one more time. And see if it is secure from cross-site scripting attacks. See, as you can see, scan alert summary, we have nothing found, so that's a good sign. So we've secured both web applications from cross-site scripting. So how did we do that? We did that by sanitizing. We could do more layers of sanitization by input data type validation, by validating the request method, email, password, usernames, checking for empty strings, emails, URLs, integers, booleans. In Python, we can use packages such as Flask or Request Validator to do this same. Whitelist programming. Let us see a whitelist programming function. So let us assume the hacker does something like this. He changes, converts this to hexadecimal and tries to inject this code into the web application. So this code here converts hexadecimal to plain text. Let's have a look into it. So save that and we run the application. So it says script alert.1, that is the same as over here. So this is what we converted from text to hexadecimal. So and we've got the same thing. Now this could turn into an attack if properly handled, that is if all these white spaces were taken away. We will do so. So it is the same code, we've just taken away the white spaces. Now let's run this again, and it says localhost 1. So we can still do a reflected cross-site scripting attack by hex values. So this is very dangerous. So this is where the whitelist filtering comes into play. So we will feed the same to the whitelist filtering function and see what happens. This is a simple whitelist program written in PHP. So the whitelist states all characters that are to be accepted. Any characters that are not in a whitelist will be neglected. So look, let's say something like that, and let's run this. So all the characters which were not there in the whitelist got sanitized. So let's run the same code. So all the script tags were stripped away, so we are safe from the reflective cross-site scripting attack. Now let's say the attacker wanted to Unicode his text such as this. So let's try that too. So let's take something from here. So we take that and we feed it to the whitelist filtering program or function, and we save that and run this program. So nothing was given, meaning it fully sanitized the whole string. Let us try one other Unicode and see if this attack still works. I'm sorry. Okay, let's save that. Run this again. Oh, and it says only one, because the rest of the characters got stripped away or sanitized. It is not a good idea to use whitelist filtering or input data type validation, as they cannot be relied on as a primary method to prevent cross-site scripting, but if implemented properly can reduce the impact of the attack. So to summarize this, never trust user-generated data. All user-generated data must undergo strict type, character and encoding enforcement to prevent the attack. Sessions must be specific for every host, meaning every user should have his or own session. By doing so, we could prevent cross-site scripting. Thank you. Stay home, stay safe.